Now, when I do this, I'm going to rotate this. I'm like physically going to rotate my graphs. So on my when I'm drawing this, I should draw my frame like this, and I should draw my frame twice. This will be my shear. This will be my moment. And then on my diagram, I would draw it like this. And I'll show you what I mean by this in a moment. Oh, and then there's a question of what is this value? This value is equal to and what is this length? This length is L over 2. So I'm going to plug in L over 2 here, and I get L squared over 4. So this value here should be L squared on 4. This value here should be L squared on 4. Let's see what CD looks like. So in CD, I should actually say CDE. Is this force going to the left or to the right? This force is going to the left. P equals WL over 2. I have some force, dy. Again, I know this is a negative value, but I'm keeping my sign convention the same way as I had it before. So if I make a little cut here, I should get v of x and m of x. Now, as I'm doing these equations, what is my v of x? My v of x is going to be plus dy equals 0. This is sum of forces in the y direction. I have no other forces in the y direction. My v of x equals negative dy is going to be equal to negative of negative WL, and that's hardly legible, isn't it? My blue marker has had it. Negative times negative WL. This is going to be positive. My v of x is going to be positive WL. My moment equation is going to be... Now here it gets interesting. I have to take into account both of these forces. Let's do this way positive. M of x minus, and this is always about the cut. I'm taking the moment about this point. Minus P times L over 2. This distance is constant. It doesn't change. Right? If I take the cut here, it's still L over 2 away. This force still acts L over 2 away. If I take the cut here, this force is still L over 2 away. This force, however, does change distance. This is going to be minus dyx. And I'm going to set these equal to 0. I'm going to solve for m of x. And I should get that m of x is going to be equal to WL squared on 4 minus WL on minus WLX. These are my equations for my shear and moment for CD, the portion of the graph between C and D. Now, what is the value at x equals 0? X equals 0 is point D. When this is x is being measured from here. At x equals 0, I should get... What do you remember about this? This happens to be the same value we got here. So our moment diagram around a corner should be the same. It should be constant around the corner. Going from the top down, I got WL squared on 4. Going from here, looking at this point from this cut, I got WL squared on 4. That is what it means to be a fixed end. Your moment transfers across the joint. Okay, so that's my moment and at 0. And let's just check what happens when I'm at L over 2 away. I end up getting, well, you can check the math yourself on this, but I end up getting WL squared on 4, negative WL squared on 4. Let's draw the graphs for this problem, for those two lines. I'm going to again draw my section. It looks like this. This is C, that's C, this is D, this is E. My graphs will be something like this. My v of x is going to be positive here, so it's going to be positive here. This is my moment. Let me make my moment convention positive downwards again. This is my equation. I start off with the positive value at x equals 0. So at x equals 0, I have a positive WL squared on 4. At x equals L over 2, I should have a negative L squared on 4. And I connect these two with a straight line. Right? Because this is a straight line. The x is to a single power. This is negative, this is positive. Okay. So that's all easy, but then how do I actually draw this on the diagram? It's very, very simple. I'm going to draw, this is my frame. My frame looks something like this. I am going to draw, I know what this graph looks like now, and I know what this graph looks like now. So I'm just going to draw those two graphs that I have so far. On this case, I'm going to make my, it doesn't matter as long as I label what the sign is on here. So it doesn't matter if I draw it above or below the axis. But I'm going to draw it something like this. I should get negative shear down here. This is going to be negative WL on 2. On the right side, on the left side from C to D, I'm going to get this. So I should get something that looks like this. I'm drawing it directly on my frame. I don't need to draw the loads on here. I'm just drawing that. Now the moment diagram is going to look something like. I have to draw the frame again, and I should get something that looks like. Oh, it should end at 0. It's going to be positive, so I'm going to draw positive this way. It's going to end at WL squared on 4. Down here, it's going to end something like this. Sorry, this is negative. This is negative WL squared on 4. This is positive WL squared on 4. And again, these two values are the same. And now you need to draw this portion and this portion. Okay, I think that covers just about every part of this problem. I tried to go through it extremely quickly, and it still took me 21 minutes, and I have no idea how on earth Professor Ledford does so many problems in a single class setting. But I guess one day I'll have to pick his brains about that. But yes, let me know if you have any other questions on this problem.